Welcome to Unit 6, Chemistry, the mole. How do chemists measure particles? Well, let's start by imagining how many atoms of carbon are in a 1-carat diamond. So if you're picturing a very large diamond on a woman's finger, how many atoms might be in there? And the answer is about 10 sextillion, I think this is, atoms. And so that is a very, very, very large number and not particularly useful or practical when we are doing math problems in chemistry, especially if we're talking about one atom at a time. So because chemists focus heavily on tiny particles like atoms and electrons and protons, they use a quantity called a mole to make calculations more manageable rather than dealing with these very large numbers in something that can be seen by the naked eye. A mole is a quantity of 6.022 times 10 to the 23rd particles. And particles we use to refer to atoms or molecules. So this is a mole in chemistry. 6.022 times 10 to the 23rd particles. Remember, this is scientific notation where this is 6.022 and then that number is multiplied by 10 23 times. So we're actually moving the decimal over 23 times from this point in order to get that total quantity of particles in a mole. A mole in Latin means huge pile. So that's how we came up with this name. Chemists came up with this name. And the mole, and this is our abbreviation for mole. Don't ask me why, they just decided to take one letter off, but this is the abbreviation for mole, is a unit that is a bridge between the atomic world and the macroscopic chemical world. So what do I mean by that? Well, this is a 5-gram sample of nickel sulfate. So here we have an ionic compound of nickel sulfate, which we can clearly see. It is made of 1.95 times 10 to the 22nd nickel sulfate molecules, individual molecules or particles, which we cannot see. So if we were to discuss how many molecules were in this sample of nickel sulfate, we would be able to use the mole in order to talk about how many particles or how many molecules were in this sample that we can see, even though we can't see all the individual particles within it. So that's how the mole allows us to bridge the gap between the atomic world, which is very small, and the chemical world, which we can see with our eyes. Who figured out how many particles are in a mole? Well, in 1811, an Italian scientist named Avogadro was studying gases and theorized that equal volumes of all gases at the same temperature and pressure contained an equal number of particles. In honor of him, 6.022 times 10 to the 23rd is known as Avogadro's number. So if these balloons were filled to the same volume, but some contained helium gas and some contained nitrogen gas, they would still contain the same number of atoms. And so we discussed this number of particles in a mole, and we call that in shorthand Avogadro's number. So how exactly do we convert particles to moles or to something visible using Avogadro's number? Well, there's a couple of steps here. First step, identify your known quantity. This is your starting place. So this would be generally how many moles you have, could be how many particles you have, And we'll get into some other known quantities a little bit later in the course. Then you determine the conversion factor needed for the units given, and this is always going to involve Avogadro's number. And we check that units being converted cancel out, because when we're using dimensional analysis, we cancel out units. One of the units is on the top, one's on the bottom. As long as they match, they cancel out. And then we solve and verify significant figures. So let's see what that looks like. How many moles are in 8.35 times 10 to the 23rd atoms of calcium? So if we had this many atoms of calcium, how many moles would we visibly be able to see? So our known quantity here is the 8.35 times 10 to the 23rd atoms. And because calcium is an element, we're discussing atoms instead of molecules. But either way, we're talking about very, very small particles, so we're going to use Avogadro's number. So now we're going to determine the conversion factor needed. So we're converting atoms into moles. Moles is our unknown quantity, atoms is our known quantity. And so we're going to start with the known of 8.35 times 10 to the 23rd atoms. We're going to put that over 1. And then we're going to include our conversion factor. And the conversion factor here is that 1 mole of any substance is equal to 6.022 times 10 to the 23rd particles of that substance. And here we're talking about atoms since we're talking about an element. So 1 mole of calcium is equal to 6.022 times 10 to the 23rd atoms of calcium. Since we have atoms on the top here, we need to put atoms on the bottom here, and that allows us to cancel those units out, leaving us with the mole, which is what we want for our unknown quantity here. We're going to multiply across the top, multiply across the bottom, and then divide the top divided by the bottom. And it gives us 1.39 moles of calcium, which is what we were looking for in the question, so we are finished. So we're starting with our known quantity, using a conversion factor that matches up with whatever this known quantity was, so that we're putting that same unit on the bottom. So moles could go on the bottom here, or atoms, but because we had atoms for our known quantity, we need to have atoms on the bottom for this conversion factor. And then multiplying across and dividing. And our sig figs here, we are not including this 10 to the 23rd in our answer. So 8.35 has 3 sig figs, and so 1.39 is going to be our answer there with 3 sig figs. So let's practice again. How many atoms are there in a 1.25 mole sample of chlorine? So I want you to try this on your own. When I'm finished with the explanation here, pause the video and try it. But let's start here by saying how many atoms is going to be our unknown is atoms. 1.25 moles of chlorine is our known quantity. So we're going to start with the 1.25 moles of chlorine. Use your conversion factor so that the moles will cancel out, and then multiply across and solve using your 3 sig figs for 1.25. So pause the video, try it on your own, and then come back and check your answer. Okay, so we are starting with 1.25 moles of chlorine over 1 times, and then we use our conversion factor here. This time we're putting moles on the bottom because we had moles on the top for our known quantity, and so we need to cancel those out by putting moles on the bottom here. So that leaves us with atoms on the top because there are 6.022 times 10 to the 23rd atoms in every 1 mole of chlorine. And we're going to cancel those units out, and our answer is going to be 7.53 times 10 to the 23rd atoms of chlorine. 3 sig figs, 3 sig figs, and so we're finished. So in summary, the mole is a quantity that helps chemists identify atomic amounts using macroscopic measurements. 6.022 times 10 to the 23rd, Avogadro's number, is the number of particles in a mole. Let's get into how is atomic mass different than molar mass. So we've talked about atomic mass in the past. The mass of an element listed on the periodic table is the average atomic mass for a single atom of that element. And we've discussed how the average atomic mass for a single atom of a particular element is measured in AMUs, or atomic mass unit. So that's the average mass for an atom of a particular element. And we've discussed how we take the average of all of the isotopes to come up with that. So the atomic mass is measured in AMU. And the molar mass is the mass in grams of 1 mole of a substance. And numerically, the molar mass is equal to the atomic mass, but this time we write it in grams. So whereas 12.01 AMUs would be the average atomic mass of a carbon atom, we now say that 12.01 grams of carbon is equal to 1 mole of carbon. So we use the same number to measure 1 atom of carbon as well as 1 mole of carbon. So how is molar mass determined? Well, the molar mass of a single element is the atomic mass in grams, as I just said. So you just read that off the periodic table. The molar mass of carbon is 12.01. And any other element that you're reading off the periodic table, the atomic mass is going to be listed for you directly on the periodic table. The molar mass of a compound, however, is the sum of the atomic masses of the elements in the compound, also in grams for our units. So if you were to ask to find the molar mass of carbon dioxide, for example, we have 1 carbon atom in this molecule and 2 oxygen atoms. So we take the mass of 1 carbon atom, 1 times 12.01 grams off the periodic table, and that gives us 12.01. There are 2 oxygen atoms, so we take 2 times 15.99, and that gives us 31.98. And if we add the mass of all of those atoms together, that will give us the molar mass of carbon dioxide, 43.99 grams of carbon dioxide per 1 mole of carbon dioxide. So that's what molar mass means, the mass per mole, 43.99 for carbon dioxide. So do these as practice. Pause the video, find the molar mass of aluminum, sulfur, and aluminum sulfide. Okay. The molar mass of aluminum is 26.982. That came directly off of the periodic table. Molar mass of sulfur is 32.066, again off the periodic table. And the molar mass of aluminum sulfide, Al2S3, is 2 aluminum atoms, so 2 at 26.982 grams gives us 53.964. And 3 sulfur atoms gives us 3 times 32.066, or 96.198. Add those together and we get a molar mass for aluminum sulfide of 150.162 grams per mole. And the molar mass can be used to convert moles to mass or vice versa. For example, what is the mass of 2.56 moles of calcium phosphate? So here's the formula for calcium phosphate. Our first step is to calculate the molar mass of calcium phosphate. So we have 3 calcium atoms, 3 at 40.078. This came from the periodic table. And we've got 2 phosphorus, 2 times 30.974, again from the periodic table, and 8 oxygen atoms. 8 times 15.999 gives us 127.992. And again, remember that we calculated this by saying that there are 2 phosphorus atoms here because the subscript 2 is on the outside of the parentheses. So there are 2 of this entire polyatomic ion. So all of this combination here, there are 2 of them. So there's 2 phosphorus and then there are 8 oxygen. We multiply that subscript through. So adding up all of these numbers, we get 310.174 grams for the molar mass of calcium phosphate. So what is the mass of 2.56 moles of calcium phosphate? This is the mass of 1 mole of calcium phosphate. How do we figure out what 2.56 moles of calcium phosphate is? Well, we use our known quantity from the question, 2.56 moles, and we use our conversion factor of 310.174 grams per 1 mole for calcium phosphate, because this is the molar mass. So that means this amount of mass per 1 mole. And we put the moles on the top here, so there's going to be moles on the bottom here. That's how we know which way this conversion factor is written. And we're going to cancel those moles out, multiply across the top, and it'll give us 794.054 grams of calcium phosphate. And since we have 3 sig figs as our least number of sig figs in this problem, we're going to reduce this to 3 sig figs, 794 grams of calcium phosphate in 2.56 moles. So in summary, 1 mole of an element is equal to its atomic mass units in grams. To find the molar mass of a compound, add the molar masses of the total atoms of each element. The molar mass can be used to convert moles to mass or mass to mole. When we're discussing moles, we often discuss STP. So what is STP? Well, as a reminder, Avogadro's hypothesis states that equal volumes of all gases at the same temperature and pressure contain an equal number of particles. So we called those particles a reference point for the mole. But we need to talk now about what are those volumes and temperatures. Since gases are mostly empty spaces between particles, temperature and pressure greatly affect the particle movement. So there's a lot of space in between these gas molecules in this balloon. And that means that these molecules have the ability to move, and their movement is based on the temperature and pressure in the balloon. And we'll get into a lot more about these specifics later in the course. But for now, just understand that temperature and pressure have a pretty big effect on the space that a gas takes up. So look at how the volume of this hydrogen gas changes when the temperature increases. So at a low temperature, it doesn't take up as much space. The molecules are not moving quite as rapidly. At a higher temperature, the molecules are moving much faster, and that causes them to take up more space, and it makes the balloon larger. So the volume changes based on temperature and pressure. So when we're discussing number of particles, it's important that we are discussing a standardized number, and so we used STP for that to help us standardize what exactly we're talking about in amounts of gases. So to compare gases, scientists use standard temperature and pressure, or STP. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere, which is very close to what you would experience around your body from air pressure. What is a molar volume? So the molar volume of a gas is the volume of 1 mole of a gas at STP. So 1 mole of a gas at STP is 22.4 liters. So that gas, whatever that gas is, 1 mole of it at STP will always take up 22.4 liters when we're discussing standard temperature and pressure. So if we look at an illustration here, we have, let's say, a balloon that has helium gas in it, we have a balloon that has nitrogen gas in it, a balloon that has methane gas in it, and 1 mole of these 3 gases at STP has the same number of particles because they all contain 1 mole, and 1 mole is 6.022 times 10 to the 23rd particles, no matter what gas we're talking about. But they have different masses. So if we hold the volume and temperature and pressure all the same, because it's at STP, which is standardized, the number of molecules or particles is going to be the same for each of these because they each contain 1 mole, but the mass is going to be different because there are different atoms involved in these gases. So how do we use STP for molar conversion? So this is a conversion factor, and we can use dimensional analysis to calculate the volume of gases at STP. For example, how many moles of neon gas will occupy a volume of 165.5 liters at STP? So the at STP tells us it is 22.4 liters per mole. So we're going to start with our known quantity, which is the volume of 165.5 liters of neon. And we're going to put that over 1. And then we want, since we have liters up at the top here, we're going to put liters at the bottom. And our conversion factor is 22.4 liters per mole. We're going to cancel out our liters. And that will give us 7.388 moles of neon. So we're again multiplying across the top, multiplying across the bottom, and we're going to divide top number by bottom number. Conversion factors like 22.4 liters are not used to calculate sig figs. So we're not going to pay attention to the fact that there are 3 sig figs in this conversion factor because it is just a value that we're using to change our original measurement. And so the original measurement is the sig figs that we need to pay attention to. So 165.5 has 4 sig figs, so our answer is also going to have 4 sig figs. So practice this one on your own. Again, we're using this conversion factor here. You can flip it whichever way you need to in order to solve for your unknown. What is the volume of 2.65 moles of krypton gas? Pause the video here until you calculate. So we're starting with 2.65 moles of krypton. That's what's given to us in the question. And we're going to multiply that by our conversion factor. Here we had to flip it from the one above so that we could get moles on the bottom since we're starting with moles. And these need to cancel each other out. Top over here, bottom over here gives us the ability to cancel out moles. And we end up with liters remaining. 2.65 times 22.4 gives us 59.4 liters of krypton, 3 sig figs, because we started with 3 sig figs in our measurement. So in summary, Avogadro's hypothesis says that equal volumes of gases at standard temperature and pressure contain an equal number of particles. Therefore, STP can be used to compare gases using molar conversions. So why are we spending so much time talking about the mole? Well, the mole is a quantity that we are going to continue to use throughout the rest of the year, and it's sometimes known as the heart of chemistry. So why exactly is that? Because the mole allows chemists to quantify and compare the amounts of material in different samples. It is sometimes known as the heart of chemistry. So for example, if you were to look at different medications and whether you were able to take those at the same time and they might have harmful interactions, the key to understanding the interactions between these pharmaceutical substances is an understanding of moles. The mole helps to link conversion factors together. So we've talked about several conversion factors at this point. We've discussed the volume of a gas and that volume at STP. We've discussed the number of particles in a mole, atoms or molecules, and we've discussed molar mass. And the mole helps us to link all of those conversion factors together. So we can convert from particles to moles and moles to particles by using Avogadro's number, 6.022 times 10 to the 23rd. We can convert from moles to mass of a substance or mass to moles by using the molar mass. And we can convert from volume to moles or moles to volume at STP by using 22.4 liters. So the mole helps us to actually link these different conversion factors together. We can determine what the mass of a substance is if we know its volume, because we can convert from volume to moles and then moles to mass. So this helps us to link these different conversion factors together. So how exactly do we combine these? What does a problem look like? Well, we're going to start, as always, with the units given in the problem. Then we're going to convert to moles, and we're going to convert then from moles to whatever the desired units are. So our example here, what is the mass of 2.79 times 10 to the 25th molecules of H2O, or water? So our known quantity here is the number of molecules, and we are trying to convert to, or trying to find, the mass. So if we look back at our conversion here, we know the number of particles, so we're going to use Avogadro's number and this conversion factor to convert to moles, and then we're going to convert from moles to mass using the molar mass. So that looks like putting the known quantity over 1 using dimensional analysis, as we have been doing. And then we're going to get rid of this set of units here, which molecules counts as particles. And so we're going to use Avogadro's number here. And we're going to put that on the bottom, 6.022 times 10 to the 23rd molecules in 1 mole. So this is our conversion factor. And that allows us to get rid of the molecules units. Now we are at moles, but we want to get to mass, so we need to convert further. So we're going to use another conversion factor, and in order to get from moles to mass, we need to use the molar mass. So we're going to put moles on the bottom here, and we are discussing water, H2O. So there are 18.015 grams of water in every mole of water, and that is the molar mass. So we took the mass of 2 atoms of hydrogen and 1 atom of oxygen, and that became our molar mass here at 18.015. That allows us to eliminate moles as a unit, since we have it on the top and the bottom here. And we're left with grams, which is mass, and that's exactly what we're looking for. So we're going to now multiply across the top, divide by the quantity on the bottom, the product of all of those on the bottom, and it will give us 835 grams of water. So 2.79 times 10 to the 25th molecules of water is going to weigh 835 grams. So this is allowing us to convert from one quantity to another using that mole amount. So let's do 2 more practice problems. How many molecules are in 1.35 liters of helium gas? And I'm going to let you figure this out on your own. So just pause the video and use your conversion factors. Go back and look at that heart diagram if you need to figure out how to convert from liters into molecules. Okay, and now we're starting with 1.35 liters of helium gas. If you didn't write the gas here, that's not a problem. And we're putting that quantity over 1 because this is our known value. We're going to multiply that by 22.4 liters of helium per 1 mole. And this is going to be at STP. So we're going to use that 22.4 liters. Allows us to eliminate that helium. And then we're going to eliminate the moles units by using our conversion factor to get to molecules, which is Avogadro's number 6.022 times 10 to the 23rd. And now we've eliminated moles and we're left with molecules. Multiply across and divide, and we get 3.63 times 10 to the 22nd molecules of helium. So check your answer on that one, and then we're going to practice another. How many grams would Max need to measure out in order to have 5.50 times 10 to the 24th atoms of gold? So again, pause the video, do your calculations, and then come back and check. Okay, so we're starting with our known amount here, which is atoms. That is a type of particle, so we're going to use Avogadro's number. And we're going to put that on the bottom, moles on the top, which allows us to eliminate atoms. And now we're going to convert from moles to grams, and we need to use the molar mass for that. So 196.967 grams per mole of gold. And gold is just a single element, so we can use the molar mass from the periodic table. And when we multiply across and divide, we end up with 1,798.93 grams, which can be converted into 1.80 kilograms, which gives us the same number of sig figs as we started with. So in summary, the mole helps to link conversion factors together, so it is known as the heart of chemistry. Two-step conversion problems involve converting from a given measurement to moles and then to the desired unit. How can a chemical formula show mole relationships? Chemical formulas show the ratio of atoms in a molecule. You already know that. These formulas can be used to convert from moles of a compound to moles of an element. So here's an example. A mole of water has 6.022 times 10 to the 23rd H2O molecules in it. So this whole molecule, one mole of that whole molecule. Since there are 2 hydrogen atoms for every one H2O molecule, there are actually 2 moles of hydrogen for every 1 mole of H2O. So if we want to see how many moles of hydrogen are in 3 moles of water, we take 3 moles of water, and there's 1 mole of water, 2 moles of hydrogen for every 1 mole of water. So we cancel those out, multiply across, and we end up with 6 moles of hydrogen. So for every 3 moles of H2O, there are 6 moles of hydrogen, which makes sense because the ratio here is 2 hydrogen atoms for every 1 water molecule. We also discussed this type of process when we're talking about percent composition, but instead of using moles, we're discussing mass. Percent composition is the percentage of mass a particular substance or element has within a compound based on mass. So let's take a closer look at this, and I think it'll make more sense than the definition. So if we want to find the percentage of an element in a compound, we take the mass of that element in the compound and divide by the mass of the total compound. So this is exactly the same process that you would be using in math to find the percentage of something. the partial over the total. And then we multiply that by 100, and that gives us the percent. These iron ore pellets are a combination of iron mixed with a binding agent. They're used as fuel for furnaces and usually are made of 64 to 72% iron. So the percentage varies. The formula above could be used to help you determine the percentage of iron in these pellets. So let's do an example here, or a practice problem. What is the percent of lithium in lithium oxide? So our first step here is to find the molar mass of the whole molecule, whole compound. And we do that by finding the mass of lithium times 2, since there are 2 atoms of lithium, and the mass of oxygen. We add all of that together, and that gives us the molar mass of the whole compound. So the molar mass of lithium oxide is 29.881. That's our total. So if we wanted to find the percentage of lithium here, we're going to take the lithium portion and divide by the total. So we take 2 times the mass of 1 mole of lithium, which we're finding the atomic mass on the periodic table. So 2 times 6.941, and that's our lithium mass divided by the total, times 100 gives us 46.5% lithium by mass in this whole compound. So just because there's a ratio here of 2 to 1 does not mean that the mass is 2 times as much for lithium. In fact, it's about half. And then because oxygen is a heavier element, it is going to take up that other half of the mass here. So our percentage doesn't always align with the ratio. In fact, it almost never does. So practice this one on your own. What is the percentage of each element in silver sulfate? So you're going to start by finding the total mass, molar mass of the compound by using the subscripts here and multiplying by the mass of each element. So find the total, and then you're going to break it down and do the mass of silver, the mass of sulfur, and the mass of oxygen. And again, don't forget to use those subscripts. So pause the video here, practice that on your own, and then come back and check it. Okay, so our molar mass of silver sulfate is 311.798 grams. Depending on what periodic table you're using, this could vary slightly, which should be pretty close to that. And then to find the percentage of silver in that, we take 2, since we have a subscript 2 here, times the molar mass of silver, and divide that by the total, times 100, and we get 69.191% silver. The percentage of sulfur, we only have 1 sulfur atom in this molecule, so we just use the molar mass once. 32.066 divided by the total times 100 gives us 10% approximately sulfur. And then the percentage of oxygen is going to be 4 times 15.999, and we get the 4 from that subscript and the 15.999 from the periodic table for the mass of oxygen. Divide by the total times 100, and we get 20.525% oxygen. These percents should add up very, very close to 100. In theory, they definitely should add up to 100, but depending on how you rounded them, they might be just kind of close. So that is percent composition. Let's look at hydrates, which are sort of an offshoot of this percent composition conversation. As some salts crystallize from a water solution, they bind water molecules in their structure, creating a compound called a hydrate. So they actually as they crystallize, the water molecules are bound within that compound. Sodium carbonate, here's our formula for sodium carbonate, forms a hydrate that has 10 water molecules for every 1 molecule of sodium carbonate. Its formula is written as this for sodium carbonate and then 10 water molecules. So let's do a percent composition question for a hydrate like this one. Find the mass percentage of water in sodium carbonate decahydrate, so we put a prefix here for the 10, which has a molar mass of 286.19 grams per mole. So this is the molar mass of this entire substance here. I want you to find the percentage of water. So we're going to start with 10 moles of water because there are 10 moles of water per 1 mole of sodium carbonate. And then we're going to use the molar mass of water to convert this to grams because we are discussing the mass percentage. So we need to convert here to mass first. And so we're going to cancel out moles and we end up with the mass of water in this compound, which is 180.15 grams. And then we're going to take that partial mass and divide by the total mass of the whole substance. So we use 180.2 and divide that by the total molar mass times 100 gives us 62.948% of water in this hydrate. So that's a more complicated type of percent composition problem. So in summary, chemical formulas show the ratio of elements within a compound. These formulas can be used to show the percent composition by mass of each element. Some compounds also incorporate water into their structures, creating a hydrate. What is an empirical formula? So we've been talking about percent composition so far, and the percent composition is used to determine a compound's empirical formula. So let's say that you were experimenting with a certain reaction and you ended up with this substance that you determined was 40% iron and 60% sulfur. How could you use that information to determine what is the compound formula for the substance that you've created? So we're going to go through this process here. An empirical formula consists of the symbols for the elements combined in a compound, with subscripts showing the smallest whole number mole ratio of the different atoms in the compound. So this is just like a typical chemical formula, but instead of the real numbers for the number of atoms in the compound, it is showing you a ratio, the smallest whole number ratio of the different atoms in the compound. For example, CH2O is giving us the empirical formula here, telling us that there's a ratio of 1 mole of carbon for every 2 moles of hydrogen and 1 mole of oxygen. So this would be the empirical formula. Now, that formula may or may not actually be CH2O for that substance. It could be C2H4O2, and that would still give us the same ratio of 1 carbon to 2 hydrogen to 1 oxygen. And so this is the smallest ratio. These are the smallest subscripts that you can come up with for a formula for a particular substance. And let's go through exactly how we calculate an empirical formula. First of all, we're going to take the percentage of mass, the percentage of composition, and we're going to convert that to mass. So assuming that there's 100 grams of the compound, if there was a percentage of 40% iron, there would be 40 grams out of 100. And so it's very simple to convert from percentage to mass because they're going to be the same number. Then we're going to convert the mass to moles for each of the elements. Then divide the moles of each element by the smallest mole answer. And if the answer is not a whole number, if it has a decimal, then we're going to multiply all the answers by the smallest whole number, which makes the ratios whole numbers. So this is a very complicated way of saying this process. But these are the 4 steps, and we're going to make this a little bit simpler and then go through an example. So don't get overwhelmed yet. So here is a simple way to remember it with a memory poem, since it's got a lot of steps to this process. Percent to mass, mass to moles, divide by the small, so the smallest mole number, we're going to divide by that, and then multiply to make them all whole. So because this rhymes a little bit, maybe it'll help you remember how to do it. Percent to mass, mass to moles, divide by the small, multiply to make them all whole. So let's go through an example of how this works. What is the empirical formula for a compound that is 15.8% carbon and 84.2% sulfur? So first of all, we're going to convert percent to mass. So if we have 15.8% carbon, we're going to make that 15.8 grams of carbon out of 100, theoretically. And then we're going to convert to moles. So we use the molar mass of carbon to do that. And we're putting grams on the bottom here to cancel them out. Gives us 1.32 moles of carbon. Then we're going to do the same thing with sulfur. So we've come up with the moles of carbon. We're going to do the same thing for sulfur, 84.2% converted to grams, convert to moles, and calculate it out, and we have 2.63 moles of sulfur. So we've now converted to moles, and the next part is divide by the small. So our smallest number here is 1.32. So we're going to divide both of those numbers by 1.32, and we end up with 1 for this and 2 for sulfur. So we have 1 mole of carbon for every 2 moles of sulfur, and that allows us to make the empirical formula of CS2. There are 2 moles of sulfur for every 1 mole of carbon. And when you're determining the chemical formula, the least electronegative atom is written first, or element. So carbon is the least electronegative. We're going to put that one first. Sulfur comes second. In summary, the empirical formula is the smallest whole number ratio of the elements in a compound. It can be calculated from percent composition by converting to moles. So what is the molecular formula? As I mentioned, the empirical formula does not necessarily show the correct number of atoms in a compound. It gives us the ratio of atoms, but it doesn't show us necessarily the exact number of atoms. The empirical formula and the molar mass help us determine the correct molecular formula, or true number of atoms in the compound as it exists in nature. So the empirical formula is a ratio, our smallest ratio, and the molecular formula is the actual number of atoms that you would find based on that ratio. So both of these molecules here, formaldehyde and glucose, have the same ratio of atoms, 1 to 2 to 1. Here we have 1 to 2 to 1. And so they actually have the same empirical formula, but they have different molecular formulas. As you can see, the formulas are quite different. The molar mass of formaldehyde, though, is 30.03 grams per mole, and the molar mass of glucose is 180.15 grams per mole. Because it's a much larger molecule, it has a much larger mass. So if the molar mass of the compound is the same as the molar mass of the empirical formula, then the empirical formula is the same as the molecular formula. So if the smallest ratio is the same as the molar mass of that ratio, then it's going to be the empirical formula. For example, if we have a ratio, an empirical formula of CH2O, and the mass adds up to whatever this adds up to, that's going to give us exactly the same formula. If, on the other hand, the molar mass of the compound is not the same as the molar mass of the formula, so if we add up our molar mass for CH2O and that's not the same as the molar mass that's given to us for the compound, then the molecular formula will need to be calculated. So if this mass does not equal whatever the molar mass was, then we're going to have to calculate that additional ratio. So how is the molecular formula calculated then? Well, first we determine the empirical formula. And we already established how to do that. That was the convert percentage to mass, mass to moles, divide by the small, and make it whole. So once we calculate the empirical formula, then we use a given molecular molar mass and the formula here, the molar mass of the molecular formula, so the whole compound, divided by the empirical formula, or the smallest ratio, and that will give us N, which is the number that all of those subscripts need to be multiplied by. So in our example here, N would be 6. We're multiplying all of these elements by 6. So all of these subscripts. So C1 times 6 gives us C6. H2 times 6 gives us H12. And O1 times 6 gives us O6. So that's how we're calculating the number to multiply that by. And then we're going to multiply all of the subscripts in the empirical formula by that N value to determine the molecular formula. So let's do an example here. You were able to determine that a compound which consisted of 56.38% phosphorus and 43.62% oxygen has an empirical formula of P2O3. The molecular molar mass of this compound is 219.9 grams. What is its molecular formula? So you've already used these percentages to calculate the empirical formula. Now you have the empirical formula here, and you have the molecular molar mass, or the full molar mass of this compound. And so we're going to divide the molar mass of the empirical formula, the molecular mass divided by the empirical mass. So 219 is our molecular mass divided by the empirical formula mass gives us 2, and that's our N value that we're going to use to multiply all of those subscripts by. So 2 times P2O3 gives us a molecular formula, or a true formula here, for this compound of P4O6. So in summary, the molecular formula for a compound represents how the molecule exists in nature. It is determined by using the empirical formula and a given molar mass.